Hi folks, we are on the Unit 1, Day 3, and we are on video number 2. So if you haven't seen the first one, make sure you go back and watch that. Some of our lessons are going to be a little bit longer and broken up into 2 or 3 videos. So we're talking about adding and subtracting vectors. This is a first example of adding vectors, and there's a couple really important notation things and ideas in here, but on the whole, I don't think that you will mostly find this very difficult. It's just a few things to be careful about. So we have vectors u and v, where the angle between u and v is 35 degrees, and the magnitude of u is 5. Remember, that's the magnitude signs from last lesson. And the magnitude of v is 7. We want to determine u plus v. So I'm going to point out a couple things right from the start here. This angle between u and v is really important that you label it correctly. Whenever we say the angle between two vectors, that always means the tail-to-tail angle. So this angle between is always tail to tail. And that can be a little bit tricky to remember, I guess, because that's not actually how we add vectors. We add them head to tail. But whenever you're given an angle between two vectors, that means if you have one vector there, you line them up, that they're starting in the exact same spot, that angle between is the theta that would be located in there. So that's always how we describe and label the angle between vectors. The other piece of this that unfortunately I often have people miss this on an assessment no matter how many times they say it, so please don't be the one who gets half marks on an easy question, is that if I say determine u plus v is a vector. This is a vector answer. So you need, what does a vector have? A vector has magnitude and direction. So if I say find a vector, find an answer, and that answer is a vector quantity, I am not on a test or on a quiz going to say find the magnitude of u plus v, find the angle of u plus v. You need to be responsible for knowing that any vector quantity, you have to find both of those. If it doesn't specify, like if it had the magnitude signs here, that would be a different story. But if it just says to find that vector, you have to realize that it's a vector and find both parts of the vector quantity, the magnitude and the direction. So those are the really, I guess, a little bit tricky things that you need to watch for when we're doing this. But other than that, basically this is going to be grade 10 trigonometry. Like if you can do sine law and cosine law, you're all set. So first thing, you need to always draw a vector diagram for any vector addition questions. So I'm going to start out with my vector diagram, and I'm going to draw vector u going up there. I probably should use a ruler because that was a little wobbly. And then I'm going to draw vector v, it's a little bit longer, out there. And this is obviously not really super well to scale, but that's okay. And I'm going to label my angle between as that 35 degrees. So you may have already kind of spotted an issue here that if we are labeling the 35 degrees in there, this is not actually a diagram of how vector addition works. We need to add vectors head to tail, but we need to label the angles tail to tail. So I need to translate one of these vectors, I'll pick vector v, and translate it up this way so that I can have my resultant or sum. I'm going to draw a new vector in here and label that u plus v. Okay, so I have a triangle here and I know the magnitude of u is 5. So on this side, it's going to be a 5. And the magnitude of v is 7. And I want to find the magnitude and direction of that pink resultant vector. Now, we're going to have to translate the angle that's given, the 35 degrees, into an angle that I can use in the triangle. And I know that these two, the v's, will be parallel because they're the same vector. So I'm going to have to use my grade 9 geometry and think about the C pattern here, that this angle up top would be 180 minus 35. So that's 145 degrees. So you will have to kind of refresh yourself on that C pattern, F pattern, Z pattern. C is the most common, but Z comes up too for sure when we are working with parallel lines to help us get an angle in the triangle. Now, if your vector diagram gets a bit messy, there's nothing wrong with saying, I'm just going to redraw this and make it a little neater and label a 5 and a 7 and 145 degrees. And I might put an X there. The X is the magnitude of the sum of u plus v. So here we know we could find this. We can find that X value using the cosine law. So 5 squared plus 7 squared minus 2 times 5 times 7 times cos of 145. So when you are doing this, I don't need to see a lot of steps. I'm not real interested in whether you can figure out or show a bunch of work about using cosine law or sine law. I would just like to see the actual final answer for these. So when you're doing this, again, you just kind of, I want to see the formula, what you're using filled in there. And then I also want to see your final answer to 2 decimal places. So I get 11.46 there, but you don't need to show any other work. This would be probably 2 marks, like 1 for setup, 1 for the right answer. You don't need to show a ton of steps there. Now, I also need to be able to describe the direction of my vector. So I have the magnitude here. U plus v has a magnitude of 11.46. And the direction, I'm going to put in reference to my vector u. So I'm going to put in an angle theta there. And then I will solve for this theta using the sine law. So I know because I have this really big angle up top, I'm not going to have an ambiguous case. Like I for sure can't have an ambiguous case if one of my angles is already greater than 90 degrees. So I'm going to pop this into the sine law to find my theta. So sine theta over 7 equals sine 145 over 11.46. And you could also use the cosine law, but I think most people prefer sine law to find these. So again, I don't need to see a lot of steps in solving here. If you put that into the formula and then do the work of figuring out your angle, I get theta as 20.51 degrees. So I don't need to see all of your cross multiplying or anything else in there. Just show me the formula you're using with the numbers in it and then the final answer, and that's all good. Okay, so now we've got the angle. This 20.51 would be this angle in between u and my resultant pink vector of u plus v, and we know the magnitude. So I'm going to summarize that u plus v is 11 0.46, and it's 20.51 degrees. And this part tends to be a little tricky for people. It's from U, so I'm measuring that 20.51. And we can kind of think, maybe I'll redraw this here. If this was U, this would be the U plus V, and then this was V. So that's how they would all be. Remember, angles between them are always tail to tail. So my 20.51 degrees is in there. So that's 20.51 degrees away from U, but there's two different ways that could go. That could also go up here, and that's not the way it is. It's 20.51 from U towards V. So you should be able to find a unique spot for that vector to be. So I measured 20.51 degrees away from vector U, and it's going towards V, not in the other direction. You maybe could have gotten, if you had done this differently and drawn a different diagram from the start, you maybe would have had whatever the 35 minus that 20, so you could have had like 14 point something if you had found that other angle down there and drawn your original diagram a little bit differently. But hopefully that makes sense. And that's a complete answer because I have the magnitude and the direction. If we're talking about subtracting vectors, there basically isn't a way of subtracting vectors. All we're going to do is add a negative vector. So if we were doing 5 minus 3, that's actually the same as 5 plus negative 3. If we only have addition, but we have integers, we don't even really need subtraction. And that's how it works with vectors. So if we wanted to do V minus W in this diagram, here's V and here's W, the first thing you do is draw in a negative W. So the opposite vector to your positive W, and then we're going to translate that negative W at the head of V. So we're going along V and then in a negative W direction. From there, it's going to work the exact same way. So it's just a matter of, are you drawing the negative of the vector or the positive of the vector at the head of the first vector. So this is a case where you might have a Z pattern, say you had that angle theta. With subtracting vectors, you do often end up with a Z pattern in there. So here we've got vectors A, B, and C. Just kind of a sketch of adding 3 vectors. It is a little bit tricky to do, and typically if you were actually doing the calculations, you would want to, you would have to do these really just kind of 2 at a time, but it is possible to figure out a resultant vector here. So A plus B minus C. So I'm going to try and do as accurately as I can. There's vector A. Let's see if I have a black pen here for C. And then I'm going to go plus B, so that's going to go in the same direction as B. And then the C is going to be in the opposite direction. So I'm kind of freehanding this, but hopefully, and I think it would go a little bit past, and that's negative C. So my resultant vector is actually not very big. Sometimes you'll add vectors and get a much smaller result than what you started with. That orange vector would be A plus B minus C in that direction. So if you kind of add up all of those, so it's like going along positive A, positive B, and then negative C, where did you start from and where did you end up? You draw in your new vector there. Okay, The last example I'm going to do in this video deals with this cube, and it is going to be important that we have a cube here. And so all of these are going to be the same magnitude. And we've got our A, B, and C labeled as GH, GC, and GF. And we want to rewrite these vectors in terms of A, B, and C. So you'll remember that these vectors have magnitude, they have direction, but they don't have location. So this A here is also the same as FE, and it's also the same as BA, and it's also the same as CD. It doesn't matter where that vector is labeled. Any vector that you draw that's the same magnitude, same direction, is the same vector. So the first one, if we go HD, we're starting at kind of an easy one. So HD, what vector is that the same as? HD is the same as GC because this is a cube. So that's vector C. Okay. Now AB, they do get a little trickier. So AB goes along this way. That's the same, looks kind of the same as A, but it's going in the opposite direction. So AB has the same magnitude as A, but it's going in the opposite direction. So that'll be negative vector A. Okay. GE, so going from G to E, this is a diagonal that we don't have a single vector that describes that direction. But remember, we can look at vector addition. So we can go along the A and then along from H to E, which is the same as my vector B. So this is vector A plus vector B. And the last one, HF, would be similar. We're starting at H, we would go negative A because it's in the opposite, plus B. So you have to kind of look at how these go through this direction and where they get to. I'm going to try one last one that's a little bit trickier. Let's try BH. And think about how we would get from B down to H. And I'm going to sketch it in here where that would go, like through the middle of the cube there from B to H. That looks kind of like a C because I drew it on top. So to get from B to H, I have to follow along these edges where the A, B's, and C's are. So I could go B to C along this, which is like a negative B. And then I could go down here, which is the opposite of C, so negative C. And then I could go from the G to the H, which is plus vector A. So negative B minus C plus A, and any order of that would also give you going from B to H. So you can do between really any of the coordinates of this cube. I think I'm kind of pushing it in length here, but I did want to take a look at a proof. So, because I want to talk about proper proof format. So here we've got this same cube and we want to prove, this is called the associative property, that A plus B together added with C is equal to A plus B plus C together. So that basically it doesn't matter what order you add up these vectors in, that it's going to be the same. And that's pretty intuitive. Like I feel like most people would be okay with that. That most people would be pretty comfortable saying, well, that's just like numbers, right? If you did that with any real numbers or any kind of values that you've worked with so far, that's true. It's not true for all number sets though. So we need to kind of prove that it would be true for vectors. So we're going to prove this in terms of this cube, which is a limited proof for sure. So whenever we're asked for a proof, we're going to look at a left side, right side, which you guys have probably seen. I know you have lots of times, but mainly with trig. So I'm going to prove it in terms of this cube. So here, and this is going to seem a little ridiculously meticulous, but it's to kind of point out the type of format and the type of rigorous mathematical explanation and proof that you need to provide. So A plus B in here, I'm going to call that GH plus GF. And then plus C is GC. So I'm just kind of converting these into the other format. Now GH plus GF, I can't add those because they're not head to tail. What could I replace GF with to make this head to tail? I could call that HE. So GH plus HE and I know that I can put those equal because it's a cube. And you maybe want to state that say GH is equal to all of the A's that are equal. FE is equal to CD is equal to BA. So those are all vector A. And then the ones that are all vector B, GF is equal to HE is equal to DA is equal to CB, and those are all equal to vector B. So this is kind of stating the stuff we know because it is a cube. So we know that the edges of a cube will all be the same length, and they will all, those kind of corresponding edges will all be in the same direction. And then we're going to use this as well. GC equals FB equals EA equals HD, and that's all equal to vector C. Okay. So here, now I've got this a little bit summarized. GH plus HE, now this is something I can add, and that goes from G to E. So now they are head to tail, and then plus GC. Now GE plus GC, those are not head to tail. I have to change this GC using one of these that will make it be head to tail. So we have GE plus GC. I want to go EA as a substitute for this GC vector. And I've listed those off as being all equal, so I can use that equality. So G to E, then E to A, that's equal to GA. I'm going to do a similar thing on with the right-hand side and add these. So GH plus, now my B is GF plus GC. And I'm going to add these bracket first. So GH plus, make sure you keep in all of your vector signs, GF plus GC. These are not tail to tail, but if I substitute FB as equal to GC, and don't forget my vector signs, then I can add those tail to tail. That's G to F and F to B goes, whoops, plus GB. Now G to H plus G to B. What's an equivalent one going G to B? That would be H to A. And we get GA. So we have worked this out using the definition of the cube, using those equivalent vectors, and doing these in the order that the brackets indicated. So left side equals right side, therefore, and we should write this out, A plus B plus C equals A plus B plus C. A little bit squished at the bottom there.